Hello, folks. Welcome to part 14 of Learning Rust from Scratch. And I'm Karuka, and let's continue with the Rust language book that we were looking at. And basically, now we're looking at the Boolean type, and we'll go back to looking at the appendix B once the Boolean type is done for all the operators that Rust provides. So, in most programming languages, a Boolean type in Rust has two possible values. Um, so, true and false. So, Boolean are one byte in size. So Boolean type in Rust is specified using a bool. For example, true, false, that's all right. Explicit type annotation. So the main way to use Boolean is through conditionals such as an if expression. We'll cover how if expressions work in Rust in the control flow section. Okay, awesome. So I think this will be the next one after functions and counts. So Rust's char type is the language's most primitive algebraic type. So here are some examples of declaring char values. Z, capital Z with explicit type annotation, and you can even have a emoji. Note that we specify character literals with single quotes as opposed to string literals which use double quotes. So char type is 4 bytes in size and represents a Unicode scalar value. Okay, great. Which means it can represent a lot more than just ASCII. So it's not just 1 byte, it's 4 bytes. So accented letters, Chinese, Japanese, and Korean characters, any Unicode, I think UTF-8. Let's check it out. So emoji and zero with spaces are all valid character values in Rust. Unicode scalar values range from U plus 4 zeros to U plus D7FF and U plus E triple zero to U plus 10 4Fs, right? So inclusive. So however, a character isn't really a concept in Unicode. So it's really not a concept, isn't really a concept in Unicode. So human intuition for what a character is may not match up with what a char is in Rust. We'll discuss this topic in detail in storing UTF-8 encoded text with strings in chapter 8. So chapter 8 is actually, I think, strings. So let's see what it is. Chapter 8, common collections. Storing lists of values with vectors, storing 888 encoded text with strings. Great. So compound types, so these are user-based types, I think. So can group multiple values into one type. Compound types can group multiple values into one type, so it's like all one unit. Has two primitive compound types, one is tuples and another is arrays. I'm wondering if struct is actually a thing. Let's see. So a tuple is a general way of grouping together a number of values with a variety of types. So in Golang, I don't know if there's a tuple concept. I don't remember it having a tuple concept, but I know Python has a tuple concept, and looks like even Rust has it. So we created a tuple by so one moment. So a tuple is a general way of grouping together a number of values with a variety of types. So different values, different types into one compound type. Tuples have a fixed length. Once declared, they cannot grow or shrink in size. So it's not an array. So it's a fixed size thing, and it's a tuple. So we create and tuples can have different variety of types. An array, I think, can have only one type. All the values can only be of one type. So we create a tuple by writing a comma separated list of values inside parentheses. So each position in the tuple has a type, and the types of the different values in a tuple don't have to be the same. We've added optional type annotations in this example. So 32-bit integer, 64-bit floating type, and unsigned 8-bit integer. Variable tuple binds to the entire tuple because a tuple is considered a single compound element. To get the individual values out of a tuple, we can use pattern matching to destructure a tuple value like this. So you just say x, y, z and get it. This program first creates a tuple and binds it to the variable, and so it should be 6.4, I think. Variable tube, it then uses a pattern with let to take a tube and turn it into three separate variables x, y, z. This is called destructuring. This is similar to, I think, JAS for destructuring objects and all, because it breaks the single tuple into three parts. Finally, the program prints the value of y, which is 6.4. So we can also access a tuple element directly by using a period by saying dot zero. Okay. followed by the index of the value you want to access. Great. So this program creates a tuple, it creates a tuple X and then accesses each element of a tuple using their respective indices. As with most programming languages, the first index in a tuple is zero, similar to first index in an array is zero. Uh, so the tuple without any values has a special linked unit. This value and its corresponding type are both written as unit, this parenthesis, and represent an empty value or an empty return type. Expressions implicitly return the unit value if they don't return any other value. So the array type, before we go here, we can actually see the parenthesis over here, I think. Where is it? Oh yeah, empty tuple, also known as unit, both literal and type. This is the actual value, the literal, and the type. This is parenthesized expression. If you want a tuple of size 1, then you need a single comma at least over here. Single element tuple expression. Single element tuple type. Oh, tuple type and tuple. There are interesting things here. You can do, you know, dereferencing of a expression, and then you can do raw pointers. I don't know what these are. Forward pointer type. On types, you can do these things, interesting stuff. So I think these are mentioned in the function arguments or wherever this is necessary to mention the type that is going to come, type of an expression, um, borrowed pointer type. Interesting stuff. So, and you can actually see member access, this dot indentation and all, and ranges, struct literal update, and the rest pattern bindings. So, variant x, struct x, dot, 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 okay. Variant is actually a enum thing around. So, and then this one expression deprecated use dot dot equal to this is I think right inclusive range literal. So inclusive range patterns and then division assignment constraints. This is the type annotation and constraints. So struct field initializer and then a loop label and this is to label a loop. Okay. Do you have go to statements? I don't know. The statement and item terminator, okay, that is semicolon. So part of its size array syntax, providing the length, I think. Left shift, right shift operation, left shift and assignment or two, and then less than comparison, less than or equal to assignment or equivalence, equal to comparison, and then greater than and equal to or greater than comparison. So part of match arm syntax, this is arm syntax, and then greater than or equal to, um, and then right shift assignment, pattern binding and listing. Caret, bitwise exclusive OR, and then assignment, and we have the OR pattern alternatives, bitwise OR, and then bitwise OR and assignment, and then logical OR short circuiting. So if this is zero, this will be evaluated. If this is one, this is not evaluated. Error progression. Okay. Non-operator symbols. These are operator symbols. Non-operator symbols are interesting. Named lifetime or loop label. Okay. Something to check out. ASCII, byte literary, character literal, and whatnot. There are many symbols to check out. I'll come back and check it out. So we have the array type now that we still haven't looked at. So another way to have a collection of multiple values is with an array. So unlike a tuple, every element of an array must have the same type, and unlike arrays in some other languages, arrays just have a fixed length. Okay, so other languages they can have variable length or fixed length. I think variable length is called slice in Golang. Fixed length is just called array, but in Rust looks like they have a fixed length only. We write the values in an array as a comma separated list inside square brackets. So this is it. And the type I think is infer. Arrays are useful when you want your data allocated on the stack, the same as the other types we have seen so far, rather than the heap. We'll discuss the stack and heap more in chapter 4, or when you want to ensure you always have a fixed number of elements. Uh, so an array isn't as flexible as the vector type though. A vector is a similar collection type provided by the standard library that is allowed to grow or shrink in size. If you're unsure whether to use an array or vector, chances are you should use a vector. Discusses vectors in more details. Chatrate has vector, hash maps, strings, and vectors. Right. So, however, arrays are more useful when you know the number of elements will not change. You not need to change. For example, if you are using the names of the month in a program, you would probably use an array rather than a vector because you know it will always contain 12 elements. January, February, March, April. So it says allow and use. That's why this is being allowed. So you write an arrays type using square brackets with the type of each element, a semicolon, and the number of elements in the array, like so. So the type is mentioned like this, but if it's already there, it can be inferred also. Here, integer 32-bit is the type of each element. After the semicolon, the number 5 indicates the array contains 5 elements. You can also initialize an array to contain the same value for each element by specifying the initial value followed by a semicolon and then the length of the array in square brackets as shown here. Then the array named A will contain 5 elements that will all be set to the value 3 initially. This is the same as writing 3333 5 times, but in a more concise way. Accessing array elements, so square bracket setting, block brackets. An array is a single chunk of memory of a known fixed size that can be allocated on the stack. You can access elements of an array using indexing like this. A of 0, A of 1, and all. So instead of dots, you use of 0. In the example, the variable name first will get the value 1 because that is the value at index 0. And at index 1, it will be 2. And invalid array element access. Let's see what happens if we try to access an element of an array that is past the end of the array. Say you run this code similar to the guessing game in chapter 2 to get an array index from the user. Please enter an array index and you type, say, 0, 1, 3, 5. So you just say 5 or 6 or something. This code compiles successfully. If you run this code using Cargo run and enter 0 under the code, program will print out the corresponding value of that index. If you instead enter a number past the end of the array, such as 10, you'll see the output like this. If panic, index out of bounds, the length is 5, but the index is 10. Okay. Run with just backtrace and then variable to display as backtrace. Backtrace. The program resulted in a runtime error at the point of using an invalid value in the indexing operation. The program exited with an error message and didn't execute the final print line statement. When you attempt to access an element using indexing, Rust will check that the index you have specified is less than the array length. So if the index is greater than or equal to the length, the Rust will panic. This check has to happen at runtime, especially in this case, because the compiler can't possibly know what value the user will enter. The user can enter any value and they run the code later. This is an example of Rust's memory safety principles in action. In many low languages, this kind of check is not done, and when you provide an incorrect index, invalid memory can be accessed. Rust protects you against this kind of error by immediately exiting instead of allowing the memory access and continuing. So, Chapter 9 discusses more of Rust's error handling and how you can actually write readable, safe code that neither panics nor allows you invalid memory access. So chapter 9 is basically about safety, I think, error handling, unrecoverable errors with panic, or recoverable, unrecoverable errors with result, to panic or not to panic. Interesting stuff. So I'll move on to the next chapter in the next video. I'll send this one. Bye bye.